Okay, so we're going ahead here with RC circuits, and that is capacitor in AC circuits. Follows through essentially the same format as we did when we looked at inductors in AC circuits. And so I mentioned this before, but as we approach capacitors, what we can do is we can simply look at it in terms of every time we've determined a value of XL, we know that a value of XC for a capacitor is going to be directly opposing that or opposite to it, and it would be the same for inductor current to capacitor current, and the same thing for capacitor power to inductor power, and the same thing for voltage. So they're always 180 degrees out of phase. So just as an example, if we have determined already that XL was a plus J component, we would have to say with that 180 degree relationship then, simply by that XC, which is indicating capacitive reactance, would be minus J, right? So if we said that VL was plus J, that means VC would have to be minus J. What about current? If we said IL is minus J for current, that means IC would have to be plus J for current. So remember, we had that acronym that helped us remember the voltage current relationship for inductors as ELI, which indicated the current will lag the voltage by 90 degrees for a pure inductor. When it comes to capacitance, we have ICE. And what does that mean? That means that if voltage is still the reference, then we have current leading the voltage by 90 degrees for a pure capacitor, and we'll see that as we take a look at this presentation. So I just kind of wanted to start with that. Now remember, a inductor's reactance comes from its own magnetic field. When it comes to a capacitor's reactance, it comes from that electrostatic field, that building of the charge across its plates. And we saw when we left off in our last presentation that resulted in current reaching a maximum value first, and then as the capacitor charges, it reaches its steady state condition of voltage being maximum and current being zero. So, okay, let's take a look at this then. So when a capacitor is placed across an AC source, the current will vary at the same frequency as the source. So there, what we're really saying is that with the source frequency and motivating force of a sine wave at 60 hertz, that there's no doubt that the resulting current, if this is E source, the resulting current is going to be a 60 hertz sine wave as well. The only thing is because of reactance, we wouldn't expect these to be in phase like they would be for a resistive circuit. So whenever we have reactance, there's always going to be a phase shift of angular displacement between the voltage and the current. And this is something we call the circuit phase angle, right? So if we had a purely resistive circuit, R as our load, that means our phase angle is going to equal 0 degrees and everything's going to be in phase. If we were to look at an inductor, right, an L, pure inductance, then our phase angle is going to be 90 degrees. We're going to have a 90 degree shift between voltage and current. So let's see what it looks like when we look at a capacitor. So here's where we see the phase shift relationship for a capacitor, of which we can remember this relationship of which values leading or lagging the other by the ICE acronym. And we should see that's consistent with what we see here. So if we look first of all at the voltage here on the top, we can see a sine wave there where it's starting at 0 degrees. Okay, so we've got the voltage starting at 0 degrees. If we look at the current here, notice how the current is reaching a maximum at 0 degrees, and the voltage is not reaching that maximum value until 90 degrees later. And so if we have current as the reference, we've got a lagging voltage, or if we were to take voltage as the reference, we have a leading current, right? So that's what's describing the relationship that we have here. And this is simply because of that electrostatic field and what we saw when we ended off our previous presentation. So this is what we have to understand about a capacitor, is that for a purely capacitive circuit, current leads the voltage, and for a purely inductive circuit, current lags the voltage. Okay, so what does that look like in terms of vectors or phasors? We have VC, right? We have IC, and we can see with VC as the reference at 0 degrees here, this is indicating that the current leads. So this is leading IC. So IC leads VC. Now, no doubt, we could change our reference just like we can in any circuit, and we could say, well, if IC is our reference here, that means VC is going to be down here, and we have IC at 0 degrees, and with that as our reference, we would say we have a lagging VC. So it's all determined by simply your reference, and with current as the reference, we have a lagging voltage, and with voltage as the reference, we have a leading current. But realize that that doesn't change this acronym at all. It's still describing the exact same relationship between voltage and current. Now realize this is for a purely capacitive connection. If it was resistive and capacitive load, then we would have a value between 0 and 90 degrees. So that happens for an RC circuit. We have between 0 and 90 degrees because it's somewhat capacitive, somewhat resistive. And we'll see how the value of impedances determines that. Okay, so now we're to our XC relationship, or our XC formula, and this is where we have a value in ohms. So whenever we're talking about reactance, we need to realize that we are talking about opposition when we talk about reactance. So that often becomes, for a beginner, a little bit of a challenge, but you have to be aware when you're working with capacitors, are you working with their capacitive value that is determined by its physical properties and gives you a value in farads, which doesn't change with angular velocity or frequency? Or are you working with its reactance, which is always in ohms and is its opposition and is affected or changed by angular velocity? So in our equation here, 2 pi f corresponds to our angular velocity, and we have 1 over angular velocity times c. So c is the capacitance in whole units of farads, f is our frequency in whole units of hertz, and then we have our 2 pi value for our radians. So when we determine that value, we can see that obviously as the angular velocity increases, that means XC is going to decrease. So we have an inverse relationship with frequency and reactance here. Okay, so that would mean that at infinite hertz, capacitor is a short infinite frequency. That would mean we have 1 over infinity, which is going to give us a 0 value. So we have a short circuit for a capacitor at infinite hertz, which is the opposite of inductor, and that's what we've been saying. So if you were to go to your textbook under the impedance section, you'll find some practice in calculating XC values, but as we go forward, you'll get plenty of practice in all of our examples of using this relationship to determine value of opposition and reactance. And don't forget, it's on your formula sheet as well. So maybe take a moment to locate it on your formula sheet and make sure you know where to find it. So in this example here, it's got you working with a capacitor and a frequency. This type of frequency and capacitance would be something more found in electronics, audio, or things like that, but the principle is the same. You have a value in farads here for capacitance, and 20 picofarads is the value here that's being used, and picofarads is a is minus 12, 10 to the minus 12 prefix. So when you're going to calculate that value, that's what you're going to use there. And then when it comes to the frequency, you've got 1.8 kilohertz or 1800 hertz. Just put it in the formula, use your calculator. Make sure you are using the proper engineering prefixes, because remember, it's whole units of hertz and whole units of farads that are used in the calculation to give you whole units of ohms. And if you were to do that, you could confirm you get your result here of 4.4 mega ohms. Okay, so this is using that same formula, but we've got a value of XC now and a frequency, and we want to know what would be the C value that would give us that amount of reactance. Now, the reason why we look at this specifically in our course is because this is an actual equation that's used very often when we do something called power factor correction. Now, there's no doubt when we look at power, we'll look at that in more detail, but notice how we didn't go about this process when we were doing inductors. And that's because when it comes to power factor correction in power systems, it's always done through the use of a capacitor. And if you were to think about, as an example, a circuit of which you need to balance the value of XL and XC, and you have a 60 hertz circuit, and you currently have a value of, say, XL of, say, 2K ohms. If you have a value of XL of 2K ohms, in order to correct its power and have it act like a purely resistive circuit, we would find that XL has to equal XC. So that would mean that you'd have to determine a value of capacitance at 60 hertz that, for this example, gave you 2K ohms. So then you'd be determining a C value to give you that result, and that would be the C value you would add in order to balance your reactive value. So I know that's jumping ahead a little bit, but I kind of wanted to just tell you why we're introducing the repositioning of this equation such to isolate the C value. Okay, because that would allow you to determine the C value to make XL and XC equal. So we'll be doing that when we look at power factor correction, but I just thought I'd mention that. Okay, so here's where we're looking at capacitive reactance in both series and in parallel and combination. And again, we already looked at how to handle capacitance, that is a value of farads, in both series and parallel. I just got to pause. Okay, guys, I had to address the fact that I wasn't mic'd up here. So I know the audio on that previous section might not be ideal, but I'm sure it will improve now. So when it comes to reactants, what we have to understand is we're not working with farads like we were when we looked at C total values in series and in parallel. We're looking at opposition. So when it comes to opposition is all treated the same way. If you have a series connection for opposition, you simply add them up. If you have a parallel connection for opposition, you're using sum of the reciprocals or product over sum. We need to understand that when it comes to opposition, it's all the same. When it comes to capacitance in farads and inductance in henries, we have to make sure we're paying special attention to that because they're not determined in the same way as we saw from the previous presentations. So in this part then, I'm not going to spend a lot of time on it because it's simply opposition. So based on the facts, XC is in ohms, indicating reactance. Then in series, we add it. In parallel, we use product over sum or sum of the reciprocals and so on. So what would that look like here for this example? Well, when we have capacitors in series, then we know that we use the sum of their reciprocals in order to come up with their total value. So there's a couple of different ways you could do this. You could determine C total first, and if you did determine C total, you know you'd have to go through the process to do so properly using the sum of the reciprocals. And after having C total, you could simply take that C total with your frequency of 3 kilohertz to come up with an XCT. In this case, what they did is they determined their XC value for each one, which I think is fine. And then after determining the values for each one, we know that it's a series connection of opposition. So you just take one, add it to the other, to the other, to the other to give you your total. So here's the individual values that were added together, calculated individually, and because it's a series connection, they're just added together. Okay, when it comes to this example, we know that we have capacitors in parallel, and we can simply add them up to give us our total CT value. So that's where actually in this case, that's the way I would have done it. As opposed to determining each one of the XC values and then using the reciprocal to determine XCT total, even though there's nothing wrong with that, and you can see that's demonstrated here. What you could do as well is you could add up all these values of capacitance, knowing that we have a parallel connection. So what would that be? That would be 0.1 plus 0.2 plus 0.3 plus 0.4, which I think would give you 1 farad, right? 1 farad of capacitance. And now, based on the fact you have a C total equal to 1 farad, you could determine your XCT total as equal to 1 over omega C total, and then that would be 1 divided by 377, or no, sorry, 1 divided by 2 pi, frequency 3 kilohertz, multiplied by 1 microfarad, gives you a total of 53 ohms. So there's a couple of different approaches there, one of them being to determine the XC values individually and then using this equation, or the one that I just indicated where you can determine the CT value or total capacitance and use it in the reactance equation with omega to give you a result. Just make sure you're paying attention to frequency. And in all of our examples, remember, if you're not given frequency, you're to assume 60 hertz every time. So you don't even need to ask that question. If you see frequency not given for a circuit, you're to go ahead with 60 hertz. Okay, so you got the idea then. If you were to look at your series parallel combination, you know that in this case you could add, if you want to determine CT here and use that as your method, you would have to add those two as a parallel combination. Then you'd have to use the sum of the reciprocal with this C equivalent value to determine your CT. So CT would equal 1 over C1 plus 1 over C2 plus 1 over C equivalent. C equivalent came from the product over, or sorry, came from the sum of C3 and C4. And then you're just going to take the reciprocal of that to give you your CT value. After coming up with your CT value, then it's your XCT total. Your XC total then is going to be 1 over 2 pi f CT, where the CT value comes from here. And you can calculate that out, and you should get, in this case, 872 ohms. Okay, so you can use whatever method you choose to go about determining this. And of course, in their case, or in the case shown in this example, what they did was to use the individual values of calculated XC to give you the results. Okay, well, let's take a look at our capacitors in series here in this example. If we look at our capacitors in series in this example, we know that we would have a XC1 value that comes from this capacitor C1. If you look at the second capacitor, you would have an XC2 value calculated from that value, and of course the frequency of 3 kilohertz. If we're to look at the impedance that results from this connection, because they're in series, then you would simply have an XC1 value in series with an XC2 value and connected to an AC source. Based on the fact that these two values as an impedance are simply added together, you can say XC total equals XC1 plus XC2. That's the way we handle series impedance. That means you have a total impedance of the two values added together and then divided into 25 volts, right? So that means in order to determine your current here, I total, you would simply take your 25 volts divided by your XC total, and that's going to give you I total. And based on the fact that this is a purely capacitive circuit, we know that ICE would be the acronym to describe the angular displacement between voltage and current, and we'd have I leads E by 90 degrees. Okay, so once we came up with the magnitude of that current, we know that the current would be leading the applied voltage by 90 degrees. All right, well, let's look at RC now and get moving with this. So first of all, let's look at the statements that we can make about this circuit, because we'll start there as our understanding and then move forward with our analysis. So the first thing we look at here is when it comes to a series circuit, we certainly know that I total is going to equal IR is going to equal IC. That's a law that will never change. Series connected components, the currents will all be the same and they'll all be in phase. So that's important to understand too. Not only is the magnitude all the same here, it's also the same phase, because you can't have the current at a maximum value through the resistor at the exact same time it's at a minimum value through the capacitor. We have a synchronous current, and the currents are all in phase for series connection. So when it comes to that, then we look at our first statement here that says that I total, which is the same current being shown here as equal to and in phase with IR and IC, is in phase with VR. And this is something that will always be the case. Voltage and current are always in phase when it comes to a resistive component. So that's a truth. That's a truth. We're just kind of reviewing everything we know about this circuit before we start. The capacitive current, which is IT of course, leads VC by 90 degrees. And of course we know that. We've looked at that previous in this presentation and proved that that will always be the case, is we have a ICE relationship when it comes to current and voltage in a capacitive circuit. So that will be the same here. When it comes to that common current through the capacitor, its voltage is going to be 90 degrees displaced from that current, right? Because remember, that IC value is the value that is all in phase with I total. Now, here's this next statement. It says the applied voltage is always the reference in this course. I would say that sometimes you're asked to use a reference other than the applied voltage. But in power systems, it's very, very common for the applied voltage to be your default reference. And that's because in power systems, everything's about voltage. The transmission voltage, the high voltage, the medium voltage, the distribution voltage, everything's always about the voltage, unlike other disciplines like electronics. So that being said, even though I would say we can't use that statement across every example, it's the common reference when it comes to power systems. However, there is some questions where you can be asked to use common current as the reference and show voltages displaced from there and things like that. But that statement is essentially our default for power systems, is the applied voltage being the reference. So this next statement is something that is quite specific to this example, because it's going to change with different values of R and C. But if we look at this example and our calculated value of XC and our value of R, notice how they are virtually equal. That being the case, if we have opposition that's virtually equal in a series circuit, that means our voltages have to be virtually equal, because each of the IR values is being determined by using the same value of current I total. So as an example, VR would equal I total times R. VC is going to be that same value of I total, because it's series, multiplied by XC. So there's our value of current times our opposition, our value of current times our opposition to give us that voltage. That means, based on the fact that XC and R are just about equal, that VC has to be approximately equal to VR. Okay, now that's just specific to this example. Okay, now further to voltage, what we are going to have in this arrangement is a voltage triangle that proves KVL. So just let me show you just quickly what we're talking about here. If we look at a real value of R, so this is a real value of R, its voltage, VR, is going to be plotted at 0 degrees. If you remember, VL was at plus 90 degrees here for a voltage. So when it comes to VC, it's going to be a minus 90 degree value for voltage. And the sum of the two, which will be proving Kirchhoff's voltage law, will mean that the hypotenuse of this triangle is E source, right? So we have VR equal to VC to give us a voltage triangle for this circuit, and the total value when you add VR to VC equals ES, and in this case 25 volts. But we can see how the summing of the voltage values is giving us the source voltage, just like it is for any series arrangement, only there's an angular displacement between VR and VC when it comes to a reactive circuit. Okay, so if we look at this next example here, what we're really doing is we're proving Kirchhoff's voltage law here, but we're looking at the sine waves that make up the sum. And I think I mentioned this before, instead of using sine waves to prove values in an AC circuit, we simplify that to showing each one of these sine waves as a phasor and show phasor addition to give you your total value, and it just simplifies things greatly. But even if we look at these values in the time domain, you can see that as far as the I total and the VR value, they're in phase. There's a 0 degree phase shift when it comes to those two values, and that's what we said was our first statement, that the values of resistor voltage and current are always in phase. Okay, so now if we look at comparing the current to the VC value, what do you notice? You notice that ICE applies to this relationship, and the current is leading the voltage by 90 degrees. So we know that's true as well. So what does it mean? It means that if we add up all the instantaneous amplitudes of these two sine waves, we know we're going to end up getting our E source value. But again, what are we, how are we showing this in terms to prove it? Not as the sine waves, but as phasors. So if I start with VR, notice that VC is lagging. That's a lagging relationship. We have a lagging relationship for VC. So VC is down here, and the result of adding the two together is this E source. Now notice how there's a 45 degree displacement there between VR and ES. So what does that mean? That's the 45 degrees that are shown right here in this voltage triangle, and that's all consistent with the phase shifts that we see here for our sine waves. So just carrying on with our statements here, since the resistor and the capacitor provide total opposition, R and XC, to the flow of AC current in the circuit, the total opposition, as we know, is called impedance. So again, impedance is symbolized by Z. So that means Z total, for our example, will be R minus J XC. So when we're looking at a rectangular value for a series RC circuit, its rectangular value for Z total can be expressed as R minus J XC, or what's sometimes shown as R plus, because it's still an addition of values, is plus minus JXC. They're the same thing. It doesn't matter how you show that or put it in your calculator. You get the same results. This is the one that's kind of demonstrating that, yes, you are still adding the values. It's just that you're adding a minus J component for XC. So hopefully that makes sense in terms of understanding your opposition equation for a series. So if we look here then, notice how for the impedance triangle of this arrangement, we've got a angle of impedance called phi or phi right here in this triangle that is a lagging impedance. Now remember, when you divide an impedance into an applied voltage is when you get current, right? And so if I divide a lagging impedance into a voltage, I will get a current that is leading. So let's just look at that for a minute. If I was to look at I total for this arrangement that comes from this impedance, I would have E source at 0 degrees divided by Z total at angle phi or phi. Now, notice how angle phi or phi is negative from this impedance triangle. With angle phi or phi being negative, once you divide it into your applied voltage, you would have I total at a magnitude where it comes up with a leading phase angle. So that means we're proving that ICE applies to this relationship. I think this will all become a lot more clear when I go through that whiteboard presentation summarizing it all, but this is just kind of getting the idea started. We have a lagging impedance. Once that lagging impedance is divided into the applied voltage, we are going to end up with a relationship that is consistent with what we're learning, and that is for the circuit that involves capacitive reactance like it does here, this ICE relationship always has to apply. And so that would be the case. We would have a leading current in this example. And I can actually prove this with this voltage triangle that we see in this next diagram here. This is a voltage triangle. Notice how we have VR. We've got VC. It's not being shown directly as a triangle. It's showing the phasors coming from the same zero origin. But it's still an addition of the two values that can be shown as a triangle. And so now it means the hypotenuse of this triangle, because of course VC could be shown here. The hypotenuse is what you see here is the ES value. But notice how, if we pick E as the reference, E is the reference now, we have a phase angle or a current that is leading that voltage. This is called a leading angle. Notice how it's leading that voltage. And it's leading that voltage by, in this case, 45 degrees. And that was because VR was equal to VC. So we have a phase angle of 45. Now, how did I know where to find current? How did I know current would be right here? Well, don't forget, VR and current are always in phase. You can never change that. There's always a 0 degree phase shift between resistor current and resistor voltage. So in this circuit that is series, that I total value, which is the same for all components, will be found right here in phase with VR. And that's how I could say that I have a leading current here with respect to the applied voltage as reference. So ICE does apply and is confirmed. We have ICE being confirmed there. Okay, so here's another example. You can go through and verify these values. Notice how in these examples, just in order to get you practicing all the equations and relationships. It's giving you a frequency other than 60 hertz to work with. Going forward, you'll find most everything we work with is going to be 60 hertz, but for now it wants you to understand the process of going through every step, calculating XC, using that in your analysis and so on. So again, this is series. So in series, we can add up the oppositions to give you an impedance triangle. But I do want to point out right now, this process of using an impedance triangle for Z total cannot be used for parallel. And you'll find me mentioning that a lot. And the reason I do is because, you know, when we get involved in this, quite often you forget some of the things you've learned already and realize that if you were going to show me a sum of impedances adding together to give you a total Z total for a parallel circuit, you'd be telling me that two 10 ohm resistors in parallel equals 20 ohms, and we know that's not right. So we have to use product over sum when we're looking at parallel and things like that. So let's make sure we understand that when we look at this example. So in this example, we have a parallel. And with the parallel example, we know that now our common quantity is going to be voltage. So what does that mean? That ES is going to be equal in magnitude and equal in phase to VR, and it's going to be equal in magnitude and equal in phase to VC. Now our voltages are all in phase and equal value. We're going to have a current divider now. When it came to the series arrangement, we had a voltage divider. But when it comes to the parallel arrangement, this is a current divider. So we're going to prove Kirchhoff's current law for this example. So let's take a look. The current IR through the resistor is in phase with VR. Remember, that's always going to be the case. The only difference being is now it's our voltages that are all in phase and equal as opposed to our current in series. Okay, but this is always going to be the case. Doesn't matter whether it's series or parallel. This next statement, the current of the capacitor will lead the voltage of the capacitor by 90 degrees. That still applies. It will apply every time. The voltage is the reference and all of the voltage values are in phase. ES equals VR equals VC. Correct. Those are all true statements. Okay, so what does that mean? It means that when we go about solving for unknown values here, when it comes to a parallel arrangement, the quickest way or the most efficient way to really come up with our values of voltage, current, and opposition is really through the use of a current triangle. Now, when we're using the current triangle, notice how here we have our voltage already as our reference of ES equals VR equals VC at 0 degrees. We know that one of the currents in the current triangle is going to be right in phase with that voltage, and that is going to be IR. That was our first statement. Our first statement right here said that IR and VR were in phase, and they'll always be in phase. So where do we find VR in this current triangle? It is right at 0 degrees, and IR right in phase with it. Okay? Now, what else do we know? We know that the current of the capacitor leads that voltage or its voltage by 90 degrees. So we know that we have a IC leading VC by 90 degrees. So in this example, you've got a leading value of IC 90 degrees. The total current is the sum of the currents. when it comes to Kirchhoff's current law, we add the currents together to give us total currents. The hypotenuse of this current triangle is found here as I total. Okay, so with I total as the hypotenuse of this triangle, we now have the circuit phase angle, which is the angle between the applied voltage and the current, right from the triangle. And we also have a magnitude. So that magnitude can be determined by Pythagorean's theorem, or don't forget, there's less work to do if you simply put this in as a polar value, or sorry, as a rectangular value and convert it to polar. So what would I total look like as a rectangular value? I total as a rectangular value would look like IR plus J IC, right? Because plus J, this is a plus J component. You have a plus J component of IC. Now you just convert that to a polar value, which would give you a magnitude, I total, at an angle theta. All right? So instead of using Pythagoreans, you can use a conversion to get it done in a more efficient way. So once you have a magnitude of current then and an angle, that means your Z total value can be determined by E source at 0 degrees divided by I total at angle theta. And once you make that division using your calculator in polar mode, you'll get a value of Z total at angle phi or phi. Okay? And that will be a lagging impedance. Okay, so if we go about this same process using these same values and this same frequency, notice how we have an R of 530, we have our XC of 530 again. That means these currents are going to be equal currents, because when you divide the same amount of opposition into the same applied voltage, you're going to have magnitudes that are equal. The only difference is this IR current is going to be a 0 degree angle. This IC current, IC, is going to be a 90 degree leading angle, plus 90 degree. So we have to remember that when we add the two currents together. And notice how you get the same magnitude of current, and here's the rectangular value of that I total. Here's the polar value of that I total. Okay? And you can confirm that with your calculators. Okay, so if we were to look at the current triangle for that relationship, here's the values being put right in the triangle. Remember, our values of voltage are all in phase and an equal value, so this would be your applied voltage here. And this is what's called a phase angle diagram. So I would actually prefer to call that a phase angle diagram. And so for this phase angle diagram is where we have two different quantities in the same diagram. When it comes to an impedance triangle, you have all impedances. Current triangle, all currents. But when it comes to a phase angle diagram, it's representing the magnitude of both the applied voltage and the total current and the circuit phase angle. So those are all the components you need to have. ES, I total, and theta. So here's where we have ES, here's where we have the I total magnitude, and here's where we have theta. Notice how it's indicating, in this case, a leading current. That's a leading current. And in order for us to check this and make sure it's right, obviously we want to know that ICE is the relationship that we have here for this example, and sure enough, it's confirming our current leads our voltage, and in this case by 45 degrees, and that's because we were working with a capacitive circuit. Okay, before I look into this slide here and we talk about this, I'm going to stop this presentation, allow you to work on some of those practice components, and then we'll come back to this when I do that whiteboard presentation that I promised you as soon as I get it. So that's it for this for now.